Good morning, all of you. Myself Kumotni, and my roll number is 225085. And topic for the presentation is splitting field extension, Galois group, Galois theory, theorems, etc. So, what is a splitting field? Let fx be a polynomial over field f, that is, fx belongs to f of x. A finite extension field k of f is called a splitting field or decomposition field for fx if it satisfies two properties. First, fx can be factorized as a product of linear factor over k, that is, fx can be expressed as fx is equal to a naught in bracket x minus a1 x minus a2 dot x minus an, where a naught belongs to capital F, a1, a2, a3 and an belongs to capital K. Second, if fx cannot be factorized in any proper subfield of K, that is, fx can be factorized in any field K such that F is a subfield of K dash and K dash is a subfield of K such that K dash is equal to K. Now something important to note, if fx is a reducible polynomial of positive degree over f, then there exists an extension field K of f in which fx has roots and K over f is equal to degree dot fx. If K is an extension field of f and alpha belongs to K be the algebraic of degree n over f, then f of alpha over f is equal to degree dot fx, that is equal to n, where fx is smallest polynomial of degree n and alpha is its roots. Now, what is a splitting field extension? Let fx belongs to kx. An extension field of k is called a splitting field extension for fx over k if fx splits in fx. Second, there does not exist an extension field E such that k is less than E is less than f, and f where E is subfield of f and this term is properly contained. Fx splits in E of x. Example, we have the splitting field extension of x square minus 2 over q is q of root 2. Second, the splitting field extension of x square minus 2 over r is r. Now, here are some remarks. Remark 1. If fx splits in kx and k is less than f, then fx also splits in capital Fx. Remark 2. X square minus 2 belongs to qx, has q root 2 as its splitting field extension. Q is less than q root 2, whereas x square minus 2 belongs to r of x, has r as its splitting field extension. Existence of a splitting field is known as Kroneker's theorem. Now, uniqueness of a splitting field. If polynomial is irreducible, then ideal I is equal to fx is maximal. If M is maximal ideal of R, then R divided by M is a field. If R is unique factorization domain and C is irregular, then ideal generator by C, that is, C is maximal ideal. Now theorem, let K be a field and let fx belongs to capital Kx. Let f be an extension field of K in which fx splits as fx is equal to a naught x minus a1 x minus a2 dot 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 x minus an, where a naught belongs to k, a1 dot 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 an belongs to capital F. Then k of a1 a2 dot 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 an is a splitting field extension for fx over k. Now lemma, Kroneker's theorem, existence of a splitting field extension. Let k be a field and let fx be a non-constant irreducible polynomial in kx, then there exists an extension f of k in which fx admits a root. Now let's have a proof of Kroneker's theorem. Let I is equal to fx dot f of x is irreducible in capital Kx. So I is maximal ideal of Kx and therefore capital Kx divided by I is a field. Now consider mapping Ik tending to k of x is the inclusion mapping lambda kx tending to k of x divided by I is a canonical epimorphism. Therefore, I of k is equal to k. There exists k which belongs to capital K and lambda in bracket g of x is equal to g of x plus I belongs to k of x divided by I, gives a monomorphism alpha k tending to k of x divided by I, defined by alpha a is equal to a plus I, where I of u is equal to u if u belongs to k and u belongs to k of x is a polynomial of degree 0 and lambda is onto and I is 1. Normal extension of a field. A finite extension K of a field F is said to be a normal extension of F if the fixed field of G over K comma F is F. G in bracket K comma F is a subgroup of the group of all automorphic of K. Now Galois group of a polynomial over a field. Let fx be a polynomial in f of x and let k be its splitting field over f. The Galois group of fx is the group G bracket k comma f of all those automorphism of K which leaves every element of F fixed. Now Galois extension. An extension E of F is called a Galois extension if F divided by F is finite and F is the fixed field of a group of automorphism of E. Galois theory. Galois theory of finite field is one of the most elegant theories in abstract algebraic. This theory is a composition of the theory of groups and theory of algebraic field extensions. It is applied to the theory of equations and geometry. Galois group. Let F be a subfield of K, that is K is an extension field of F, then group of automorphisms of K relative to F is called Galois group K over F and is denoted by G in bracket K comma F. Hence an automorphism sigma is in G K comma F if and only if sigma x is equal to x for every x belongs to F. G of K comma F is a subgroup of the group of automorphism of K. Artin's theorem. Let G be a finite group of automorphisms of K and F be the fixed of G such that f is equal to x belongs to K, sigma of x is equal to x for all sigma belongs to G, then K divided by F is a Galois extension with G of K divided by F is equal to G.